Hey everybody, in this video I'm going to be going over some of the fundamental reasons why atoms form chemical bonds. Okay, so you can see the learning target here in front of you. I'm primarily going to be focusing on these two sub-targets right here. We'll talk about polarity and describing the differences in different types of chemical bonds in a different video. So for right now, we really just want to focus on the fundamental reasons as to why atoms form chemical bonds in the first place. And so to help kind of guide this video and our thought processes during this video, we really want to ask ourselves two questions. First off, what is a chemical bond and why do atoms form chemical bonds in the first place? So to kind of make this abstract idea a little bit more simplified and to give you some examples, I want to start off with energy, and to start off with an example that you might be more familiar with. And this is going to be describing the role of potential energy. So consider a situation where you have a ball that is above the ground, it's not moving. How is that energy being stored in that ball? So you have kinetic energy right here, and you have potential energy just to the right of it. Now, just for clarification, kinetic energy is energy associated with an object's motion, whereas potential energy is the energy associated with an object's position or its arrangement, usually relative to something else. Okay, now, as far as this ball goes, we can see that really all of its potential energy is, all of its energy is stored as potential energy. All right, fine. So what happens if we remove that little platform directly underneath the ball? The ball falls down, it starts to move, and so you can see that the potential energy went down. Well, we know that energy can't just be lost and disappear forever or anything like that. Energy gets converted or is transferred into something else. So some of this potential energy has been converted into kinetic energy. And again, notice that the total amount of energy has stayed the same. Okay, now eventually the ball hits the ground and we see that we have no potential and no kinetic energy. Now, it's not, I don't want you to think that the energy is just gone from the universe. All the energy has been transferred to the ground, and that's heated up the ground a little bit, but it's also released in the form of sound. But from the ball's point of view, it has no kinetic energy and has no potential energy. All right, so one of the questions I'm going to ask is, well, what would be required to increase the ball's potential energy? In other words, to move it from the ground to up here. Well, I could just pick it up and I could move it there. So in other words, an external force would be required. For example, I lift it up. Okay, so due to an external force, the ball now has more potential energy. And I want that to I want to put a flag in that just for a moment, because we're going to refer back to that later on, because it might seem kind of weird. Why are we talking about this right now? In order to go from a lower potential energy state to a higher potential energy state, energy was required. Okay, and in doing so, it raised that potential energy. So the ultimate question I have from this example is, okay, how does what is the relationship between potential energy and the stability of that particular object? Now, I'm not going to come up with a straight up definition of what it means to be stable. I guess if I were to kind of define it, it would be something that if the object sort of had a preference, if I were to kind of humanize it for a second, what would be sort of the preferred state? What would be the more favorable state that the object would more likely be in? So you have two options. Either the ball is up top, ball is not moving, it's got a high potential energy, or the ball is on the ground, it's not moving, it's got a low potential energy. So, excuse me, hopefully in this case you can realize that the more preferred state, or the more favorable state, the more stable state is going to be at the ground with low potential energy. So objects tend to be more stable when they are in a low potential energy state. So what happens to the stability of the ball when an external force or some energy is applied that raises its potential energy? Well, that must mean that raising the potential energy of the ball results in the ball being less stable. So again, higher potential energy, less stability; lower potential energy, more stability. So we have one big takeaway here, which I'm just going to refer to as idea number one, and that processes that result in a lower potential energy are favorable due to increased stability. I'm not going to say that every process that occurs does so because it lowers the potential energy, because we know that's not necessarily true, like for endothermic reactions. But for the sake of the conversation, we'll say, look, lowering the potential energy is favorable because it increases the stability of that of whatever objects are involved in that process. Okay, now we can kind of increase the complexity of this a little bit and say, okay, well, how do attractive and repulsive forces affect potential energy? Because we've already established this idea of potential energy and stability, in that low potential energy results in greater stability. So since I know attractive and repulsive forces are going to be present in the atom, that's why we're bringing this up. But instead of talking about the atom right away, I want to talk about magnets. So I'm not going to be talking about electrical forces. I'm going to be talking about magnetic forces for right now. So say you have two magnets with like poles facing one another. You have a repulsive force between those two magnets. And the closer you bring these magnets together, the stronger that repulsive force becomes. And if you were to actually do this, I mean, in other words, hold these magnets in your hands, I'm sure you've done this at some point in time, you can actually feel this repulsive force pushing back against you trying to bring them together. So the closer those magnets with similar poles facing each other are brought together, the stronger the repulsive force, and we can actually feel this instability actually increasing. And so what would be required to keep bringing these magnets closer with the similar poles facing one another? Well, again, energy. So we can think of sort of a low, I don't want to call this a really low potential energy, but in terms of the potential energy that's involved throughout this particular process, we can imagine that the top scenario, where the magnets are furthest away from one another, that's going to be the lowest potential energy state in this particular scenario, and then a high potential energy, or I could just say higher potential energy as they come closer together, because we are increasing that repulsive force. Okay, now what if we flip them and we bring opposite poles, or we have opposite poles facing one another? Well, instead of repulsive force, we have an attractive force. Okay, and so as they come closer together, that attractive force starts to increase more and more. So the closer the magnets with opposite poles facing each other are brought together, the stronger the attractive force becomes. Okay, and so how does potential energy play into this? And I kind of hinted at that a couple slides ago, but now you have a little bit more visual way of seeing this. So I'm just going to focus on two scenarios. So the scenario on the top left, we have the similar poles facing one another, and they're separated at a particular distance. And then on the scenario on the right, I bring them a little closer together, and that repulsive force has increased. And what it's done is it has increased potential energy, right? And it's created a less stable scenario. So what we can say from this is we can say, okay, increased repulsion raises potential energy and results in less stability. So this is the first time that we've really connected the idea of repulsion and potential energy and how they relate to stability. Now, what if we look at the opposite scenario? So we flip the magnets, and as we bring them closer together, notice that the potential energy is actually gone down. Okay, so increased attraction lowers the potential energy. So again, we're connecting attraction to a lower potential energy, and that's actually going to cause a more stable, or result in more stability. Okay, but one of the side questions I want to ask here is, well, where did that energy go? Again, we know that the energy can't just disappear from the universe. So did it get converted into something? If so, what is that thing? And so what we take from this is just like the ball that was falling before, when you had the ball up top. When you had the ball up top here on its platform, then here's the ground. If you remove that platform and that ball, which initially had a bunch of potential energy, as it dropped down, that potential energy got converted into kinetic energy, the energy involved or associated with the ball's motion. So likewise, as I bring these magnets closer together, what you notice is once they get a certain distance apart from one another, and maybe you let go of that magnet on the right is now close enough to the magnet on the left, where those attractive forces are now able to pull in that magnet on the right and actually literally have it move and actually have some kinetic energy, so that it eventually kind of connects with the other magnet. So what we can see here is that potential energy that was lost, so the amount of energy that was right here at one point in time, so this amount of energy that was lost in terms of potential energy, that's been converted into kinetic energy. right? And we see that in the motion of the actual magnet itself. So again, increased attraction lowers potential energy and results in greater stability. So idea number one, we already covered, stating the idea that lowering the potential energy is more favorable due to the fact that it increases the stability of whatever object it is we're talking about. And then idea number two now is involving attraction and repulsion, so that attraction lowers potential energy and repulsion raises potential energy. So these two ideas are going to be fundamental to what we're going to be talking about next. Now, as we get into this next topic, here's a question that we can ask ourselves to help kind of guide us. How can our new ideas of attractive and repulsive forces and potential energy be used to explain how atoms interact with each other? So before we actually look into how atoms interact with one another, we should clarify a couple things with respect to what's actually in an atom and how that's going to play a role in our conversation. So first off, atoms are made up of charged particles we know as protons and electrons. We're gonna ignore the neutrons right now. They don't have a charge anyways, but we're just going to focus on protons and electrons. These charged particles, they do interact with one another, as well as other charged particles from different atoms. And we call these interactions between these charged particles electrostatic interactions. And if you want to kind of a ballpark definition of it, it's just the attractive or repulsive interactions between objects having electric charges. All right, so if I were to talk about the, say, attractive force between this electron and this proton right here, that's considered an electrostatic interaction. All right, so that's all. I don't want you to get weirded out by that phrase, that term. Anytime I say electrostatic interactions, that's really all I'm referring to. So consider a scenario where we have two hydrogen atoms. Again, each one has one proton and one electron. And so the question that we want to ask ourselves is, well, how would the potential energy of the two atoms change as they approach one another? Okay, so what I've done in this first example is I've put them at a particular distance from each other where any forces that are present are just barely noticeable. Okay, and you can see that at least right now at the beginning, it does in fact have some potential energy, and there's no kinetic energy involved or anything like that. Okay, so before we kind of dive into this, we have to first ask ourselves, well, what forces are present? And if so, are they attractive or are they repulsive forces? All right, so first off, we have an attraction between the proton of one atom and the electron of the other atom, and likewise for if we just kind of flip it. But then we also have repulsive forces, or a repulsive force between the two electrons of the two atoms, and then we have repulsive forces between the two protons of the two atoms. Okay, so here they are at the beginning, and the attraction is greater than the repulsion, and so they're going to start coming closer together. And so we're going to just, for the sake of the conversation, start off our potential energy, right here. Okay, so as they come closer together, and the attraction increases, the repulsion will also increase as well, but the key thing to note here is that because they're coming together, that must mean that the attraction is greater than repulsion, right? And so because of that, since we're increasing attraction, and attraction is greater than repulsion, what we can say is, well, the potential energy must have gone down, because we know we've already established the relationship between increasing attraction and that resulting in a lower potential energy due to greater stability. And so you can see right here that the potential energy has gone down, and that potential energy that has gone down, the exact amount actually, has been converted into kinetic energy, right? So this would be released into the surroundings as heat, but it would also be used to actually increase the motion of the atoms themselves. Okay, so it's really important that you recognize here that difference in sort of this bottom orange bar and this top orange bar right here for the potential energy, that gap that exists right here now, that's the energy that was lost and converted to kinetic energy. So I don't want you just thinking it disappears. Now, here's the situation that we just ended with, right? And as they come even closer together, eventually they reach a point where attraction equals repulsion, okay? And so at this point, because they are in a more stable state right now than they were just even slightly before, the potential energy has gone down even more. And just like before, when you decrease that potential energy, in this case, it's being converted into kinetic energy. So again, energy loss converted into kinetic. And so eventually atoms reach a point where their potential energy is about as low as it can possibly get. It's not going to reach, an absolute zero or amount or anything like that, or it's not going to, in other words, it's not going to go down to this bottom part right here necessarily, but it's reached a minimum potential energy. And that's the key point right here. Eventually atoms come close enough together so that, most importantly, their attractive forces and their repulsive forces are equal to one another. And this is kind of a sweet spot. And we refer to this as the lowest potential energy state. So again, going back, here's the lowest potential energy state between these particular atoms, much lower than it originally started with. This is its most stable state. And when atoms reach this point, we refer to that point as simply a chemical bond. Okay, now not all chemical bonds look like this, right? I'm just trying to make a point as to how or why rather atoms even come together in the first place, what forces are behind that, and what effect that has on things like potential energy. Because I don't want you thinking about it in terms of, well, they want to, say, share these electrons, or they want to gain one electron, or want to lose one electron, and things like that. They come together because they're attracted to one another, and then they eventually come to a spot where the attraction equals repulsion, and they do so because that is the lowest potential energy state in which they can occupy, and it happens to be the most stable state that they can be in. Okay, now this distance between the nucleus of each atom, or the nuclei of the atoms, is referred to as bond length. And I'm not going to go into detail as to how bond length can change based on different characteristics of different atoms and whatnot, but it's going to be something we're going to talk about later. So I just wanted to at least introduce it to you that bond length is nothing more than the distance between the nuclei of two bonded atoms. Okay, now sometimes people ask, well, if there's attraction there, why don't the atoms just keep coming toward each other, and in other words, just kind of crash into one another? And the reason why is, well, don't forget about those repulsive forces. As you come closer and closer together and you get beyond that sweet spot, now you have these massive repulsive forces, say between the electrons, but more importantly between the protons of one atom and the protons of the other atom. Okay, and so these massive repulsive forces, as they get closer together, are going to completely overwhelm the attractive forces, and that's going to send potential energy through the roof, and that's going to reduce stability. And again, it's due to these dramatic electron-electron repulsion and proton-proton repulsive forces as well. Okay, so you can kind of picture this in what's known as a potential energy diagram. And so then on the x-axis right here, it's called internuclear distance, right? That's just the distance between, you can think of it as the distance between the atoms. I mean, really what it means is the distance between the nuclei of the two atoms involved. And then you have potential energy here on the y-axis. And so you start here on the right, and we're going to be going this particular way. So just as we saw before, this is just more of a graphical representation of this. Say we have two chlorine atoms, and they start off, a certain distance apart. Well, as they come closer together, that potential energy, as you can see, is decreasing, and they come even closer together, and it's decreasing even more, right? But it doesn't keep decreasing forever. Eventually, they reach a point of lowest potential energy, and if some outside force, some external force, were to supply some energy to this to force them to be even closer together, kind of like when you had two north poles of a magnet facing one another, that would be very unstable. And so what that would do is that would actually increase the potential energy even more. That's not going to be preferable. That's not going to be favorable. And so what you have is this moment right here where it eventually reaches a point of lowest potential energy, greatest stability, and that is the point in which the chemical bond forms. I have the exact same graph right here, or representing the same idea. Except in green, I have the bond, or hydrogen atom and a chlorine atom coming together, and in the red, I have a hydrogen atom and a fluorine atom coming together. And we'll discuss at a later time as to why these graphs are a little bit different. What is it about fluorine and chlorine that creates this difference in the graphs itself. But again, you see this idea that they will eventually decrease their potential energy as they come closer together, and eventually they'll actually reach a point of lowest potential energy where those attractive and repulsive forces are balanced or equal. Again, the lowest potential energy state. And that, the only reason I'm bringing this up time and time again and saying it over again is that is the point at which the chemical bond occurs. All right, so we can kind of get back to our original guiding questions and say, and have at least a potential answer for them and say, well, okay, a chemical bond is simply just the point of minimum potential energy where attractive forces and repulsive forces are balanced or are equal. Now, why do these atoms do this? Well, they do this to reach a state of lowest potential energy as a result of electrostatic interactions between the atoms. In other words, due to the attractive forces that exist, say between the electrons of one atom and the protons of the proton of the other atom, and vice versa. These electrostatic forces are going to bring them closer together to lower their potential energy and eventually bring them to a distance until their attractive and repulsive forces are equivalent to one another. All right, now, the last thing I want to touch base on here is the role that energy plays in chemical bonds, because it's a huge misconception that I want to at least kind of target here for a second. So let's just cover this for a moment. A few units back, we talked about energy is required to break bonds. Okay, so this animation might seem familiar to you. If not, that's okay too. But when bonds form, energy is released. And so a lot of people actually literally think about this backwards. They think that energy is released when you break bonds. They think sort of like if you have, say, two atoms bonded together, there's a whole bunch of energy in here just sort of waiting to be released, and then when you go and break it, then all that energy gets released. And that's not how it works. And so I want to sort of start out broad at first here and say, look, to break bonds, energy is required. When bonds form, that's when energy is released. Now, let's talk about this in greater detail. So as I just kind of hinted at, the big idea here is that energy is not, I repeat, not stored in chemical bonds. All right, so then the question is, well, if energy isn't stored within the chemical bonds themselves, where does the energy come from, right? And so think about it this way. You have your two atoms. They could be whatever atoms you want. Okay, and these atoms, certain distance apart from each other, as they come closer together, we've already realized that lowers the potential energy. Well, if the potential energy is lowering, that means it's decreasing, and that energy that was lost is being converted into something, right? Well, that something is the kinetic energy. So the energy that's released during this bond formation process, all right, so going from here all the way down to here, that loss in potential energy, going from a high potential energy state to a lower potential energy state, that is converted into kinetic energy, and some of that kinetic energy increases the motion of the atoms themselves, but some of it is actually in the form of heat that's transferred to the surroundings. And right, so when we say heat is released from a chemical reaction, or at least from forming chemical bonds, and say you feel that heat on something like an exothermic reaction, that heat is from the lowering of that potential energy. So it's not like it's stored in the bonds itself. It's actually the bonds themselves aren't a thing. There isn't like when these things bond right here, there isn't energy necessarily being stored, within or between these atoms or anything like that, like as a bond. It's the lowering or the decrease in potential energy as these bonds are coming closer together, right? And so these little green arrows right here, it's not the most accurate representation in the world, but I thought it was an easier way to visualize that as they are coming together, they're releasing, or rather that potential energy that's lowered is converted into kinetic energy, and these little green arrows represent the kinetic energy that's being sort of released into the surroundings at this point. Now, what about bond breaking? So imagine you have same potential energy diagram right here, but instead of atoms, I'm going to talk about this ball at the bottom of the hill. And I wanted you to push that ball up the hill. Well, to get the ball back up the hill, you already know that you must give it some energy. So energy is required to move something from a lower potential energy state to a higher potential energy state. So that's rather intuitive. Like you would know what to do with a ball at the bottom of a hill to get it, to a higher point on that hill, or at least to the top of the hill. Likewise, just substitute the ball for these atoms. Right down here, you have a low potential energy, and up here you have at least a higher potential energy state, right? So when breaking a chemical bond, not only are you moving it, by moving it from a lower to a higher potential energy state, that's going to require energy to do so. Just like the ball moving up the hill required energy to go from low to high potential energy, same idea with chemical bonds, right? So sometimes people ask, well, but don't we burn fossil fuels like hydrocarbons due to all the energy that's contained within these molecules? And the simple answer to that is not really. No, it doesn't work like that. Again, the energy isn't stored within these chemical bonds. So say you have your generic hydrocarbon chemical reaction right here, right? So you have some hydrocarbon that is reacting with oxygen, and it's forming carbon dioxide and water. And so the key thing here to realize is that it's not that all the energy is just within here and it's just waiting to be released out into the open and then allow our society to function and whatnot. It's not there. It's the products that are formed, or the bonds that are formed when making those products from those original reactants, that the energy that's released from going from a high potential, going from a high potential energy to a lower potential energy state, that energy that's released is the energy that we used or that our society uses to function, right? So it doesn't come from within these hydrocarbons. It comes from the formation of the new bonds that form to make these particular products, right? So I know I just kind of blasted through all that stuff, so feel free to rewind and make sure you take some notes on these things, because there are several aspects that aren't really the most intuitive, and sometimes it can feel a little bit abstract. So we will get into the different types of chemical bonds and why, or what's behind an atom sort of stealing one electron versus sharing it, and things like that, and polarity and electronegativity and all that stuff. But all I really wanted to cover here is sort of the fundamental reason as to why atoms form chemical bonds in the first place, from a potential energy point of view, and then not more importantly, but on a side note, how energy is related in with respect to chemical bonds, in that energy is not stored within the chemical bonds. It is the energy that is being released as the potential energy of the atoms is decreasing. Okay, so hope that helped. Let me know if you have questions.